Welcome to the Omar Alayli podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Alayli, and today I'm thrilled to be joined by George Salazar. George is a retired NASA human-computer interface technical discipline lead and expert. George has over 40 years of pioneering experience in telemetry, communications, voice recognition, and advanced avionics. His work has been instrumental in shaping systems for the Space Shuttle, the International Space Station, and next generation space programs. George, thank you so much for taking the time to be here today.
My pleasure.
George, you have spent decades building a legacy in service of developing and improving on the interfaces between humans and modern technical systems. Could you start by sharing a bit about your role and background for those who aren't familiar with your work at NASA?
Sure, I'd be happy to. I'm going to just kind of give you a little flavor of my little bit of background. I first started out as a design engineer, and my first introduction to, let's say, human-computer interfaces was voice control systems, and I think we'll be talking about that later. Uh,
Mm-hmm.
and then I started evolving into systems engineering, and then during the time I was working systems engineering at NASA, I came across human systems, and I started to work with the human factors engineering people. So I became more involved with the human element, if you will, of system design. And as a result, several colleagues of mine, we got together and started to form what we call the human computer interface group. And then we evolved the human systems integration working group, where we contributed to the adding more detail about human systems integration into the systems engineering process at NASA. So the last few years I spent in my role as a commercial crew program, and then
Mm-hmm.
the last 3 years in terms of the Artemis program in the human lander system was my responsibility for the human computer interface aspects of both the commercial crew program as well as the Artemis program, human lander systems, both for SpaceX as well as Blue Origin.
Let's start from a bird's eye view. Human centered design is all about designing things with real people in mind, making sure whatever you're creating actually works for the people who will use it instead of just focusing on technology or efficiency. So, human system design also starts by understanding the user's needs, challenges, and behaviors. How would you explain the importance of human centric design in space exploration and space mission design to someone completely new to the concept?
Sure. That's a good question. Regarding the human-centered design aspect associated with space exploration, it's a critical component. Obviously, you've got humans operating a complex system in a very harsh environment, and so ensuring that the user interface is understandable and
Mhm.
has a lot of, let's say, safety features involved is very critical for space exploration. There's been cases on the ground where a poor design human-computer interface has resulted in tragic accidents. So
Mhm.
the whole aspect of human-centric design is critical. And let me just kind of say one other thing is that rather than sometimes they call it technology centered design, where there's a technology that's they call it very cool, right?
Mhm.
But it turns out that sometimes that cool technology is not usable for the human. So from a human centered standpoint, we look at the, as you mentioned, the needs of the human, and making sure that not only the human, not only the hardware or the machine is factored into the design of the system, but you also have to look at the task. Looking at the
Mhm.
task, looking at the machine and the human integrated collectively together to optimize that whole user interface. And so, in essence, it's a process of considering the human, considering the task, and then finding out what hardware and what software is going to be suitable for that human and for that task.
Okay. So let's zoom in now to the human system integration field. or discipline. So, human system integration can mean different things in different contexts. How do you personally define human system integration, and why is it a critical component in aerospace projects?
Okay, so yes, that's a very good question. The whole aspect of human systems integration is to factor the human limitations and capabilities into the design of the system. And
Hmm.
there's different parts, and that's why this is called human systems integration. And different industries, different agencies have different what they call disciplines. For NASA,
Hmm.
there are six key disciplines: human factors engineering, there's safety, there's habitability, maintenance and sustainment, operations, as well as training. All these
Hmm.
have, these are disciplines that collectively have to be integrated in order to optimize the performance of the system as a whole. Um, I have to say that there's two aspects to human systems integration. One is the management and also the technical aspect. So the management aspect ensures that the human systems integration folks are looking across the life cycle of the system and making sure that risk, um, training, documentation, planning, all these things are factored in as part of systems engineering. So the human
Hmm.
element is always in place. That's the management part, making sure that
Hmm.
the human element and the concerns of the human is always factored in. The second part is technical. The technical is more the performance, making sure that human performance is optimized for the task.
So, NASA has a legacy of human centered design dating back to the Apollo era. How has this approach evolved with modern technologies and the rise of commercial spaceflight?
Oh wow! So back in the old days, the technology was not all that advanced. So there was a lot of tactile switches, that were used. Uh, Starting with the Mercury program, there were 55 switches on Mercury. Fast forward to the space shuttle, it had 2,500 switches. But during that time, the evolution of software was not all that great. Obviously, the machines were slower and all that. So early on, the concern was more of safety. And I have to say that for NASA, the primary, let's say, goal or
Hmm.
factor in a space operation or space program is the safety of the crew. Secondly, is success of the mission. So early
Hmm.
on, it was more of making sure that the human could operate the system correctly. There was no thought about habitability. The Mercury capsule was very constrained, confining. The even the shuttle was very constrained and confining, and so habitability was not factored too much. And then, sustainment and maintenance, another human systems integration factor, was really not considered much for the rather for the shuttle program. And as a result, the operation cost of shuttle was quite large. In fact, a lot of our budget went into the operation and maintaining the space shuttle, and so the lack of human systems integration uh, in the space shuttle program resulted in large operation costs. And it's something the military also found out too as well. Now, fast
Hmm.
forward here to the commercial program. Commercial crew, the private sector is in the business of making money as opposed to the government that's in the business of spending money. And so in the commercial crew program, they're trying to optimize their system. So human systems integration ensures that they factor all the elements in terms of habitability, sustainment, maintenance, operations, and training to optimize the performance as well as the minimize costs. And of course, SpaceX is doing quite an impressive job in terms of maintenance and sustainment because they're using reusable spacecrafts. So it's definitely evolved over the years, just simply because they're starting to incorporate more elements of human systems integration because now we're looking at costs and we're looking at long-term sustainment.
Okay. Let me follow up on this. like NASA, ESA, a lot of the space agencies love redundancies. Does the redundancies, system redundancies, affect human system integration and how they evolve and adapt to the mission and the human component?
Yes, absolutely. So redundancy, sometimes the term is called fault tolerance, tolerate a fault or an error, if you will. And so when you
Hmm.
start factoring the human-computer interface and let's say fault tolerance, tolerate an inadvertent switch closure that should have not been flipped. Okay,
Hmm.
so what results is sometimes not only redundancy but also additional hardware, and that's the trade-off that happens between safety, redundancy, success of the mission, and all these kind of factors. Let me give you an example, like
Hmm.
firing a rocket. All right, so you wouldn't want to just have one switch and flip it, and you fire a rocket, and maybe you bump into it, and it and it fires a rocket inadvertently. You don't want that to happen, especially in a critical event. So what we do in terms of fault tolerance and safety is we do what's called arm and fire. So basically, what that means is that you arm the command with one switch or touch, but you fire with a second switch located somewhere else, and that way you do
Hmm.
a separation of the redundant systems, and you ensure that if you're going to fire that rocket, you're doing it because you want to and not because you bumped into it.
Okay.
And so that's one of the challenges sometimes in the human spaceflight is the redundancy, the safety, and of course the additional complexity and weight. But it's a trade-off that has to be done early on.
So, when it comes to human system integration, where do you see the biggest shifts in design philosophy from the space shuttle era to current programs like the Commercial Crew, like you just talked about?
Yeah. Okay. So the biggest shift is uh, more of a concern of sustainment and
Hmm.
maintenance. It's a big thing. It can be very costly to a program. There's been some commercial companies that have gone broke just simply because they didn't do a very good job about minimizing or maximizing their systems, for the human use and space operations, and it's very expensive, very expensive. So I think there's a lot more emphasis in trying to minimize the cost. At the same time, though, the trade-off, rather let's say the competing requirement is safety. So you have to
Hmm.
balance safety with minimizing costs and performance.
How do you see this evolving even further in the coming decades?
Yeah, so the evolution of HSI is definitely going to occur, and the reason for that is obviously the technology has been advancing quite a bit over the last few years. Artificial intelligence, things, touchscreens, uh, voice control is up and coming. It still has a ways to go, but all these things are coming into play, and so we we're going to have to be looking at the human systems integration element, particularly when we start going. We go back to the moon, and more so when we go to Mars. When we go to Mars, it's going to be a very small crew, maybe four people, just simply because of the logistics of trying to handle the food and water requirements for a small
Hmm.
for each one of the people for a 3 year mission. And so, what's going to have to happen uh, for, let's say, for example, for the Mars mission, it's very much Earth independent, which means the astronauts cannot depend on mission control to help them. And so, a lot of onboard systems are going to have to be in place with a lot of complexity. They're going to have to be operated and commanded and controlled by the astronauts. So the let's call it the evolution of human factors engineering, the habitability, the training aspect is all going to be critical in these up and coming future missions. So I think there's going to be obviously an evolution in all these disciplines in terms of how those are approached for dealing with this new advanced complex technologies up and coming.
Okay. Um, so let's now focus. Talk about challenges. SpaceX's Dragon capsule offers touch screens now and a streamlined layout, diverging from the traditional, as you said, switches and dials cockpit. From an HSI standpoint, where were the biggest challenges in researching and adopting such a modern interface?
Yes, one of the big, actually, there's a few challenges. One was the technology itself was primarily developed for terrestrial systems here on Earth. It was
Mhm,
not intended for the higher radiation environment up in space. And so, SpaceX, working with NASA and our radiation folks and ourselves, we had to deal with finding the right hardware that could sustain itself or handle the radiation environment.
mhm,
Touchscreen has some difficulties in terms of the screen. If it gets dirty or gets wet, it causes false touches. And
mhm,
so, one of the things that we had to do early on the onset is to look at what kind of commanding was going to be used for the touchscreen and what kind of commanding was going to be used for the tactile switches. There's actually above the three touchscreens you probably see in the internet. Right below there, there's a panel that has 33 tactile push button switches. Some of them
mhm,
have a cover on them to protect them against inadvertent uh, operation. So
mhm,
the decision was made for using the touchscreen for non-critical commanding and using the buttons for critical commanding. Now, there's only
okay.
one. There's a couple of cases where the arm command can be done by touch on the screen, but the actual activation of that command is done by a switch closure. But in order for that switch closure to occur, you got to flip a control safety panel and then press the button. That was one of the challenges: is trying to trade off uh, who's going to do what, so to speak.
Mhm,
What's the touchscreen going to do, and what's the human going to do in terms of push buttons for especially critical commanding. The other one was a little bit more. It was a little bit more challenging in terms of mindset. Was that the first astronauts on Demo 2, which was the crewed mission, they didn't like touchscreens. They were accustomed to tactile switches, right? Space
mhm,
shuttle, I want to press that button, I want to flip this and all that. And one of the astronauts, he was had a lot of reservations about touchscreen. In fact, I was in a meeting one time where he said, "Would you drive a car with touchscreen, turning left, right, touching, and all this?" And he said, "Same thing with touchscreens, because there was actually one scenario where the astronauts had to do manual commanding using touchscreens to
mhm,
operate the vehicle." Now, one of the things about the what they call manual command and control is that it's a very slow moving activity, and so they have time to recuperate. Of course, there were things in place in terms of software safety features to prevent a let's say, for example, a jet firing too long or a wrong command. There was a lot of safety protocols, if you will, in that. But trying to get the astronauts to accept touchscreens it was a challenge, and very similar to voice control. In the early years, astronauts did not like voice control; they like switches.
Interesting. Um, so, how do private companies and agencies like ESA and NASA collaborate on interface standards to ensure consistency, especially when multiple vehicles like Starliner, Orion must share certain operational protocols?
Yeah, that's a good question, and it's a challenge. Right now, at least at this point in time, or up until the time that I retired, there isn't let's call it a standard interface, if you will, between
Mhm,
vehicles. Every vehicle has their own the human computer interface. What they do
mhm,
have to abide by is requirements in safety, like, for example, the safety of uh, a prevention of an inadvertent command. Okay, so that's a requirement. How they implement it is up to them, but they have to demonstrate through testing that they can prevent inadvertent commanding. So, SpaceX, has a certain way of their human-computer interface with touchscreens and the push buttons. Starliner had a different concept altogether. No touchscreens, everything was switches, and also software. A lot of software for driving the displays for menu selection. And so
Mhm.
they were able to reduce a lot of switches on the panel, but the drawback or the complexity was adding software to, let's say, scroll through the different commands and menus on the displays. So yeah, there is no standard per se, unfortunately, at this point in time. Maybe one day they will be, but at this point, it's just a matter of meeting safety requirements and how they do it. It's up to each user.
Yeah, it's a bit disappointing because it could be a big challenge, especially if we're going to the moon. So if a spacecraft that only has switches, an astronaut has to learn on how operating that spacecraft, and then hooking up at the gateway, and then going down with the lunar lander with a touch screen.
Yeah,
That's more than yeah. That makes
yeah,
sense to have standardization.
yeah.
Okay, let me follow up here. Europe and North America have a special collaborative relationship in their space program. We
Mhm.
even share collaboration with Russia in the space program because we need to, because of the International Space Station. They're our partners. What about China? When it comes to human system integration, how much is the extent of our collaboration with China? Do we share similar standards for human system integration and human factors?
Um, I guess in the last episode, we were not collaborating with China at all. China's invented, or rather, China has developed their own space program.
Hmm.
They're leveraging off a lot of Russian technology.
Hmm.
So, I mean, one can infer what they're using as a design just based on what we know about the Russian Soyuz and
Hmm.
capsules and all that. So at this point in time, we don't have any, let's call it collaboration at this point in time, with
Hmm.
China. We do have with, oh my gosh, somewhere in the vicinity of 30 plus different countries they have signed what they call the Artemis Accord, where they're going to be participating in the Artemis program. So
Hmm.
at this point in time, we are not, let's say, partnering or collaborating with China. That could
Hmm.
change later. Right now, there's a little bit of tension going on, but things can change.
I understand. George, you co authored a paper on applying human system integration principles to voice control in spacecraft systems. Where do you envision voice activated interfaces fitting within future missions, and what are some unique risks or benefits?
Yeah, that's a good question. So back when I started pioneering voice control on shuttle, as I mentioned, there was a lot of reluctance, from the astronauts. But in the future, we're going to have to consider voice control, and not necessarily for critical commanding, but perhaps for, let's say, inquiry for non-critical commanding. And one of the reasons for that is going back to what I mentioned previously of deep space missions. The crews are not going to be very big, so
Hmm.
that means that they're going to be operating a very complex system with a very small crew. And
Hmm.
what voice control offers is an extra pair of hands, if you will, that basically can execute commands on demand, from the astronauts. Now, the challenge, though, of voice control is the technology. Even though it's come a long way from the back when I was working on it, there's still the challenges of the environment, acoustical noise. There's the challenges of variability in the user and how they enunciate, how they pronounce words. You can have a diverse crew, And whatever the reason, it's not very forgiving of accents and things of that sort. And I'm sure that's going to improve over time, but at least at this point in time, I think it's a viable option as an additional tool, especially for deep space missions, where you just have to. You're going to have to depend on something else to help you out, because you only have so many hands and eyes, and so voice control provides that extra crew person, if you will, to help them operate and navigate a complex system.
Yeah, this reminds me of this Space Odyssey 2001, HAL,
Yeah,
which is
yeah, yeah,
cool.
yeah.
So, do you think we will eventually have not an AGI but similar interfaces? How far do you think we are from achieving that?
I think we're still a ways. Yeah, yeah. Even again, the technology has increased dramatically over the years. But I mean, if I think this was about a year or two ago, before I retired. We did a quick test of Siri and
Hmm.
Alexa, and so and we found out that's how we found out that Siri and Alexa are very what's the word? The algorithms that are used are very directed in terms of
Hmm.
a specific application. It's not like you can just say anything and they can come back and answer the question. I would say things like, uh, uh, "Hey Siri, my foot hurts. Have you heard anything about Davy Crockett?" And it would
Okay.
come back, what? What? And repeat that? What? What? So it's the I mean that's the limitations right now. It's the algorithms are very deterministic. One day when we do AI, it'll start evolving over time, and maybe it'll start understanding any inquiry that is asked. But at this point in time, it's very deterministic, and so that coupled with still the limitations of the technology in the environment is another challenge. But I think we'll get there. It's just a matter of time.
Okay, great. Um, Now, to get there, we need to do research and simulations here on Earth. So, given the complexity of space environments like latency, noise, signal disruptions, how realistic is it to rely on voice control for critical tasks, and what backup systems might still be necessary?
Yeah. So the thing about latency. So when you say latency, I think about the latency of communications with ground control when they're on Mars. It's a 40-minute round trip delay, even when Mars is at the closest point of Earth. And so, in emergency situations, they cannot depend on the mission control to help them out. So that's where voice control comes into play. Again, if you
Okay.
got let's say an onboard artificial intelligent mission control system, then
Hmm.
they can inquiry the onboard system by voice and say, "Hey, whatever XYZ, we're leaking here in module 4. What's going on?" And so that's where the the onboard systems are going to be able to help them in real time, rather than having to wait 40 minutes where it could be too late, for especially critical events. So, and then of course, the noise, is going to be a factor. So it could be that the speech control system, and we did that back in the shuttle program, is a um, verify command.
Hmm.
Did you say this? Yes, I did. Okay, I'm going to execute it. And so there's safety precautions that have to be factored into voice control. Same thing with switches. As I mentioned, arm and fire.
Okay. So far, we've talked about human space system integration as from an operational perspective. How about when at one point we will have or astronauts will have personal assistants or like a personal medical AI assistant or psychologist assistant, will that still fall under HSI, or is it something else?
Well, it's a combination of HSI and medical. Obviously, and this is something that is a challenge also in deep space missions, is developing a medical database because it can be
Mm-hmm.
quite large, and so the memory aspects of it, come into play. How much hardware is required for that? Uh,
Mm-hmm.
and so the the thing about medical assistance or personal assistance
Mm-hmm.
is quite a challenge for deep space missions. Not, and of course, this is the opportunity to test all this technology
Mm-hmm.
on the moon rather
Mm-hmm.
than going to Mars and you find out, hey, this didn't work. So I tend to I kind of tend to laugh a little bit when I hear that they Musk wants to go to he wants to go straight to Mars, and I think about what a friend told me many years ago. He said, would you camp in your backyard for 3 or 4 days, and then the following week go to try to climb Mount Everest? A big difference.
True.
You first have to you have to incrementally learn what it's going to take to climb something like Mount Everest.
Mm-hmm.
And so the same thing with the moon program, Artemis program, and Mars is that the moon program is going to provide the proving ground for
Mm-hmm.
learning, living, and operating on another planet, and understanding what is the limitations of the technology. Can it handle radiation for X period of years? What happens to the person? We still don't know psychologically what's going to happen to the person that's going to be on Mars. Even though we've done long-term studies here, I've had opportunities to talk to various researchers, and they still don't know what's going to happen to the human mind a when they see Earth as a small dot. I remember talking to a Russian scientist many years ago, and he said that I'll keep this story short, but he said that they did various long isolation studies in Siberia and different parts of Russia. And so after the 1 year and a half, the test subjects come out and they interview them, and so the test subject said, "Well, we managed to stay in there for that long period of time because we ate well and we were interacted and all this kind of stuff." But on the side, unofficially, they the test subjects told this particular Russian scientist, he said, the only reason that I survived for that long period of time is because I knew I was on Earth, and one day that door was going to open and I'm going to get out. So that was the
Yeah.
motivation, as opposed to there is no door to get out on Mars. So we still don't know how that's going to affect humans.
Well, that's a good segue to my next question. You've studied parallels between deep space and deep water exploration. Could you elaborate on how HSI, human system integration, challenges these environments? What challenges these environments share, and what we can learn from each?
Oh yeah, okay. So deep water, is somewhat of a similar. Let's call it an environment, not necessarily space, but
Hmm.
it's a hazardous environment.
Hmm.
If the ship is not designed properly, it could implode, killing the people. So these deep water crafts are pretty complex. They got cameras, they got all kinds of things going on, and so and sometimes it's just one or two people at most operating these systems.
Hmm.
So the human systems integration aspect of it is equally applicable for deep water mission as it is for spacecraft. And so it goes back to the I call it the three circle Venn diagram. You got the
Hmm.
human, you got the machine, and you got the task. And what you're doing, you're trying to match the human to the machine. You're trying to match the machine to the task, and the task to the human. And so all
Hmm.
this collectively is where you're optimizing all those aspects of it to get a high performance system.
Okay. Um, in the past, the radiation test evaluation reports for commercial off the shelf graphic processing boards have highlighted certain vulnerabilities. Where do we stand on utilizing COTS or the commercial off the shelf hardware? And
Okay.
does leaning on COTS hardware bring greater risks or efficiency to space missions?
Yeah, so here's another challenge associated with COTS hardware, and this is something that I think the public doesn't obviously don't understand very well. Is that commercial off-the-shelf technology or COTS was meant to operate here on Earth and not necessarily in deep space. So companies like NVIDIA, AMD, and all these companies that develop high-performance computing systems, um, they don't factor too much of the radiation environment because
Mhm.
there's no money in it. Like I had an opportunity to talk to Nvidia, and maybe that's going to change. Is the that they call it the product model for developing products is geared for things like gaming and other aspects, and not going into deep space. And so here's the challenge: is that the high performance computing that's needed for a deep space mission that we're, let's say, accustomed to here on Earth using AI and voice control, that is difficult. When I was doing with my colleagues radiation testing of graphics processing units, they all failed
Mhm.
in
Okay.
high energy proton testing. And even worse in heavy ion testing, and going to the moon, heavy ions is quite common. And so the challenge is, how can we protect without adding a lot of weight? Because you can protect some of this hardware, but you got to use a lot of metal, if you will, to protect them. And still, it's not enough many times, depending on the kind of particle that's coming from the galactic radiation environment. So it's a challenge. It's a challenge, and as we start going deeper into space, we're going to have to figure out ways to mitigate that. Now they say, well, wait a minute. On ISS, they're using laptops. They're using AI. Blah blah blah. Well, yeah, that's true. And the only reason they can do that is because they're in low Earth orbit and they're inside the Earth's magnetic field, which the Earth's magnetic field protects to a large extent a lot of the high energy galactic radiation that could destroy not only the components but add more radiation to the to the human.
So, we often see spin offs from space technology benefiting life on Earth, especially in extreme or hazardous environments. From your perspective, what aspects of human space integration and human computer interface could most significantly impact industries like deep sea drilling or polar research, or even everyday human life?
Okay, so from the benefits of human computer interface and human systems integration for here on Earth is for companies to adapt some of those philosophies that are used by NASA and commercial crew programs companies for for developing their systems and commercial companies here on the ground, whether it's a deep water cruise ships and even military ships, is looking at uh, what HSI is going to help, how HSI is going to help them in terms of the optimizing the performance of their systems as well
Mhm.
as minimizing costs. Cost is a big thing. It's a big thing, and so you got to think about how can we how can we minimize costs. Well, the way of doing it is by as part of the systems engineering process is to incorporate human systems integration. And again, um, that's one of the drawbacks. What happened to shuttle? They didn't factor a lot of HSI, and the operation costs were through the roof, and it was just costing us a lot of money to operate the shuttle.
Okay, so let's now look into the future. If we look 15, 20 years ahead, do you envision a more autonomy and less human oversight in spacecraft operations, or will human operators remain essential for decision making?
All right. So autonomy is is kind of a interesting thing that's at NASA in terms of operating the spacecraft. Uh, the let's say the mentality of operating a spacecraft is to always provide situational awareness to the crew.
Hmm.
What does that mean? So situational awareness, and it's kind of a broad term used, but basically situational awareness is looking at the perception of what's going around, what's going on. What are the circumstances that are causing this event, and then what are the forward, let's say, forward actions that need to be done. And so
Hmm.
that's situational awareness. So yeah, you have to look at how, uh, let's say, the how you're going to benefit from HSI and ACI toward perception. Autonomy, basically, you cannot just say, take over the ship. I'm going to bed. Uh,
Hmm.
and that's why astronauts are always, there's always somebody awake on a mission,
Hmm.
and you just can't do that. I'm going to give you an example of autonomy, how it backfired. Apollo 11. I'm not sure if people know the story of Apollo 11, but when it was getting ready to land, it was supposed to be an autonomous landing. Well, Neil Armstrong looked over and said, "My gosh, we're going to land on some rocks." And so he shut off the autonomous system and he took over control and maneuvered around till he found a good spot to land. So you always have to have situational awareness of what's going on and not depend on autonomy. For some things it
Hmm.
might be okay, but again, it depends on the task, the criticality of the task. But eventually, I think I'm going to say that we will have mostly semi-autonomous systems and very little fully autonomous systems.
Commercial space expansion is opening doors to more diverse participants, like space tourists, private researchers, etc. Like tourist astronauts. How does human-computer interface adapt to users who lack the intense astronaut training?
That's a good question. So, space tourists. They're probably just going to be in there for a ride, and you're hoping that somebody's experienced on how to operate the vehicle. Now, if the pilot or commander, let's say something happens to them, you hope that there's an interface that it's very simplistic for just about anybody to take control of the vehicle and bring them back home safely. So that's
Hmm.
part of the safety aspect of it, and that's part of human systems integration. And I tell students that engineering and human systems integration, it's a lot of what if questions. What if this fails? What if that fails? What goes wrong here? How can we recover from a near disastrous event? And
Hmm.
so, yeah, space tourism is fine. And, you got these, what they call themselves astronauts that don't train and they go up on a rocket and they come back down. But, in what we call off nominal or emergency event, what's in place, to bring them home safely? It always goes back to safety. Safety is number one.
Okay. Finally, for students and professionals inspired by your work, where would you recommend they start if they want to pursue a career in HSI and space technology?
Okay, so the HSI, there's only a couple of, here in the United States anyway, there's only a couple of universities that provide, quote, a degree in HSI. Um,
Hmm.
if you're majoring in industrial engineering, you get a flavor of what human factors engineering, human-centered design is in
Hmm.
industrial engineering. So that's one opportunity. The other opportunity is there's a lot of information out on the web in
Hmm.
terms of HSI. I was involved with the development of the NASA Human Systems Integration Handbook, and that
Hmm.
it's got about 300 pages of information that could help somebody understand. what HSI is all about. And of course, there's other agencies also have some HSI, Department of Defense, and the Federal Aviation Agency here in the United States. So there's a lot of information on HSI. You have to be, uh, let's say, patient in learning
Mm-hmm.
it. Because the other piece that you have to know is you have to know systems engineering. You have to know the process of systems engineering, because systems engineering and HSI kind of overlap with each other, and they go hand in hand. And so,
Okay.
without understanding systems engineering, it'd be difficult to understand how human systems integration process flows with systems engineering.
Wow, great. Before we wrap up, could you share or would you share any resources, upcoming projects, or ways for listeners to learn more about your research and human system integration in general?
Uh, I'm not. I kind of retired from doing a lot of research. I am doing some, let's say, some let's call it home study of
Mm-hmm.
some areas that I'm interested in, and I might be working with a couple of colleagues, actually from Brazil, in
Mm-hmm.
putting a paper out on human systems integration and designing for the spacecraft. So,
Okay.
um, but yeah, I think my days of doing research and all that are pretty much over with. However, I still do outreach with students, and share my knowledge and what have you with students. So that's pretty much what I do right now.
Well, George, thank you very much for this amazing conversation. It's been an honor to have you here.
My pleasure.
And to everyone else listening, this is Omar Alayli podcast. Thanks for joining us and keep exploring.